And as we jump into this particular video, we are going to look at the idea of probability and some of the basics that go along with that. We're going to connect this to some of our work with sets. And we need to begin with what's called a sample space. Now, anytime you have a situation that involves probability, you have what's called a sample space. And the sample space is very simply the set of all possible outcomes for any possible experiment. Okay, so that's what we call the sample space. For tossing a coin, it's very simple. It's just heads or tails. Those are your two choices. If you want to spin a spinner, like this particular figure off to the right here, you've got three possible outcomes depending upon what happens. So the spinner has the outcomes of 1, 2, and 3. And you could also extend this into other things as well, like the gender of the children for a 3-child family. And what we mean by that is you could wind up having a family that has 3 girls. Or they could have 2 girls and a boy. Or they could have a girl and 2 boys. Or it would be all boys. And that doesn't entirely answer the question because it could depend upon if birth order is important here. So if birth order is important, then now we've got some more situations here because, I mean, we've got the 3 girls, of course, and we've got the 2 girls with the boy coming last, or the boy could be the middle child, or we could have an older brother to 2 younger sisters. And the same thing if there's 1 girl in the family. It could be a girl that has 2 younger brothers. You are so busted, Candace. Anyway, it could be the girl is the middle child, or the girl is the youngest of the 3. And again, we've got the 3 boys. So there's 8 possibilities there. That is if birth order is important. And it just depends upon the context of the question. So if that pops up, make sure you read that very carefully. Okay, now an event is a subset of a sample space. So if the sample space for tossing a coin is heads or tails, then one event is just the heads, and another could be just tails. So if you've got an ordinary 6-sided die that numbered 1 through 6, the events involving an even number would be 2, 4, or 6. If you're talking about a number that's less than 5, the event is 1, 2, 3, and 4. And if you're talking an event that's a multiple of 3, well, that's just 3 or 6. Those are the possibilities there. Pretty straightforward to come up with a list of outcomes that satisfy a particular event. All right, now we've got this interesting game here, and let's see if we can come up with some events here in set notation. We have a coin that is flipped until both a head and a tail appear, or until the coin has been flipped 4 times. So we need to write the following events in set notation. So exactly 3 times. So if that's the case, then there's 2 possibilities here, because the first time that you toss the coin, you're going to get a head or a tail. The second time, you have to match what you got on the first in order to keep flipping. Or on the third one, that's when things switch. So you could get 2 heads and a tail. And let's get that cleaned up here. Try that again. We could get 2 heads and then a tail. And what did I just do? I goofed it one more time. There we go. Or you could get 2 tails and a head. And that would be the situation where the coin would be flipped exactly 3 times. Now, if it was flipped at least 3 times, then you could have those situations And I'm just having a hard time writing all of a sudden. There we go. Or you could have the situation where you toss the coin 4 times. So you could get 3 heads and a tail, 3 tails and a head. You could get 4 heads or 4 tails, because the rules of the game state that you are going to toss the coin until you get 1 of each, or until you get 4 tosses in. And that satisfies that situation where you get 1 of each, or you get 4 tosses in. Okay. Now, what's the probability the event where you flip the coin fewer than twice? Well, that is going to be the empty set, and the reason why is because that's not an event. Flipping the coin just once or not at all, then you're not playing the game, or you're not playing it correctly according to the rules. All right. We might do some set operations on events, like where we have this situation here. I'd like to do a little bit of change here on a couple of these things. Worker is a Blues fan. Go Blues. St. Louis Blues hockey, of course. The worker is, let's see here, what would be that? A Star Wars fan. Why not? Okay, so let's change those around a little bit so they make a little bit more sense and apply more universally here. Let's think about workers earning the minimum wage, and they're in various categories. Maybe they're St. Louis Blues fans. I'd like to think they would be, but you never know. And then maybe they're Star Wars fans, or not. Okay, so if I want to talk about the workers that are under 20, and then I want to talk about their complement here in Part E, because remember that means complement. I mean the workers not under age 20. That would be a description of that event. For B, it would be they are both fans of the Blues and Star Wars. So they'd have both. And then for C, it would be fans of the Blues or Star Wars. Okay, so for armchair hockey fans out there, as a Blues fan myself, please, by all means, jump on the whole idea of being a Blues fan. There's plenty of room for you on the bandwagon. Okay, now we've got an interesting category here called mutually exclusive. And mutually exclusive events are if the intersection is 0. Now I've got a better way, or the empty set rather, I've got a better way of phrasing it. No outcomes in common. Okay, so let's think about the events in the prior example. That would be under 20, a Blues fan, and a Star Wars fan. Is it possible that a person could be any or all of these things? And the answer is yes. They could definitely be under 20 and be a Star Wars fan. They could be under 20 and be a fan of the St. Louis Blues, or they could be all three. So what we would say to that is these are not mutually exclusive events because they don't have any outcomes in common. Now, if I'm looking at this idea of flipping a coin and rolling a die, then yes, they are mutually exclusive, because you can roll a die and get a numerical value on that quite a bit, or you could end up with a head or a tail, and those are not outcomes in common. Now, we finally get to this idea of probability, and if you're looking at sample spaces that have equally likely outcomes, the probability of an event is defined as follows. So we're going to let S be the sample space and let E be some kind of event, which is a subset of S. Then the probability that the event occurs is the number of times it can occur over the number of items that are in the sample space. So let's think about rolling a 6-sided die here. if we want to use that sample space of rolling a six-sided die, we know that the number of events in that sample space is 6. So that's going to be our denominator in each one of these fractions. And if event E is an even number, starting right over here, then the number of even numbers is 3. So the probability is going to be 3 over 6, and all day long and twice on Sunday, that reduces to 1/2. I mean, we really only want you just to reduce your fractions only on the days of the week whose names end in Y. Just on those days alone. Okay. What about getting a number less than 7? Well, I want you to think about this. If all of the numbers satisfy that event of being less than 7, then the probability is going to be 6 out of 6 or 1. This is what we call a certain event. It is bound to happen for sure. Okay. And then we have this part C here where event G, an 8 is shown. Well, is there any way to roll an 8 on a six-sided die? The answer is, well, not a typical one for sure. So the probability here would be 0 out of 6. And the word that we use to describe that is impossible. So that's an impossible event. It is never going to happen. Playing cards are very, very common use for probability questions. And there's a lot of students who have a good understanding of playing cards, and then there are some that don't. So let me give you a quick tour through the deck. There are 52 cards in a standard deck, and they are split into 4 different what are called suits: hearts, clubs, diamonds, and spades. And it's the little icon that you see. So like that's a heart, that's a club, that's a diamond, and that's a spade, and that's what you're looking for. If you have a deck of cards floating around the house somewhere, this might be a good time for you to just lay your hands on it and go through some of the different playing cards and kind of get used to what they are if you haven't played very many card games. At the head of the deck here, the ones are commonly called aces. And then we have ace all the way up through 10. And then we have these 3 face cards, Jack, Queen, and King. And they're face cards because they have pictures of faces on them. So that's a quick little tour through the deck and give you an idea of the different types of cards. Now there are also cards that are printed with black ink, which would be the spades and the clubs. And the cards that are printed with red ink are the diamonds and hearts. So that's something to think about when you're talking about red versus black. That'll probably come up in some questions. All right, so what's the probability of getting an ace if you draw a card at random? Well, there's 4 aces in the deck out of the 52 cards that there are available. So that's going to knock all the way down to 1 over 13. If you forget how to do this, don't forget you can type it into your calculator as 4 divided by 52 and then hit the math button and then hit enter twice. And that should give you a reduced fraction. So on your TI-84, math and then enter after you punch in your fraction. That'll give you a reduced fraction, save you a little bit of time there. What's the probability of getting a face card? Well, let's count off the face cards here, and you'll notice that there's 3 in each suit across the 4 suits. So that's 12 out of 52, and that'll reduce all the way down to 3 over 13. Now, this is kind of a fascinating question here. You can get a spade, and that really should be or a heart or a 3. Okay, well, let's think about this here. We've got to be really careful with this question because there are 13 spades in the deck and there are 13 hearts in the deck. Now, if I want to get the probability of getting something or something else, I have to add those things together. So I also have to think about the 3s, and there are 4 of those in the deck. But the catch is, I've got a problem here. My problem is that I have double counted 2 cards. See, here's all the spades and hearts. And you notice that I've counted the 3 of hearts and the 3 of spades twice. I counted the 3 of hearts once here and once here. I counted the 3 of spades once here and once here. So because I double counted those cards, I have to take away for 2 of those, the ones that I double counted. So as I go to do the math, this ends up being 28 out of 52, or 7 out of 13 when we reduce down into lowest terms. All right, now the last thing is in what's called empirical probability here, and this one is kind of fun, but at the same time, it can be a little annoying to figure out. We've got some data on accidents here that occurred on recreation equipment, and it's asking us to find the probability that somebody was injured on a trampoline. Well, we can see very easily that there were 107,345 injuries that resulted from a trampoline. But in order to figure out what the probability is that a trampoline was the culprit, what we need to do is add up all of the other numbers and see what sort of percentage or ratio that the trampolines took of that. So when I add all of those together, it's going to be 903,887. And when I divide 107,345 into that number, I'm just going to do an approximation here, and it's going to be 0.118. So it's about a 12% chance that it was a trampoline that caused an injury. And this is what we call empirical probability because it's based on data where it may not be possible to establish exact probabilities. I mean, this is just maybe a sample of the injuries that occurred in recreational equipment across maybe a certain part of the country or a certain part of the world. Okay, that's a kind of a long-winded explanation into probability, but there it is. Enjoy.